Okay, this is Dr. Brown. In this video, we're going to talk about concavity and the second derivative test. We're going to look at concavity, which means if a function is concave up, it'll look like this. If it's concave down, it'll look like this. And we're going to use the idea of concavity, which is related to the second derivative, to come up with a way of finding where a function has minima and maxima. Now, let's think of the graph of a function y equal f of x that is differentiable. It's concave up on an interval if the first derivative is increasing on the interval, and it's concave down on an open interval if f prime is decreasing on the interval. Let's sort of examine that. Obviously, this is concave up just because of our definition of what a concave up graph looks like. Notice that at this point, f prime is negative. However, further down, where f prime is still negative, f prime is less negative. Therefore, we conclude that f prime is increasing. On the other side of the point where f prime is 0, f prime is more than 0 and it's positive. At this point, and f prime is more positive further up on the graph. So we conclude that f prime is increasing. And as we'll see in the statement on the next page, the second derivative then must be more than 0, because the second derivative is the derivative of the first derivative. So if f prime is increasing, the second derivative of f must be more than 0. Now look at the concave down graph. At the very beginning of this graph, f prime is positive. Further up on the graph, f prime is still positive, but it's less positive. So f prime is decreasing. On the other side of the point where f prime is 0, we have f prime is negative. And further down, f prime is more negative. So f prime is again decreasing. So because f prime is decreasing, the second derivative must be less than 0, and that tells us the function is concave down at or on this interval. So here is the second derivative test for concavity. You need to know this. If the function y equal f of x is twice differentiable on an interval I, if the second derivative is more than 0, the graph is concave up. If the second derivative is less than 0, it's simply concave down. Now let's look at some examples. Let's take a function y equal cosine of x plus 3, and the graph is shown here. And if we take the second derivative of the function, we get that the second derivative is cosine of x. You can see that by realizing that y prime is equal to minus sine of x. And the second derivative would be the derivative of minus sine, which would be minus cosine of x. Now, we have a graph here of the second derivative function, and you can see where it's negative below the x-axis, that the original function y should be concave down. And sure enough, it is concave down. Now, where the second derivative is positive, we expect the original function to be concave up, and sure enough, the function y is concave up. And then finally, when the second derivative is negative again, we are concave down again. Now, definition: a point where the graph of a function has a tangent line and where the concavity changes, like from up to down or from down to up, is called a point of inflection. Now, notice that at this point on this graph, where the second derivative goes from negative to plus, at the point, this would be pi over 2, I believe. Notice that the original curve goes from being concave down to concave up. So this is a point of inflection. I want to make a point that at many points of inflection, the second derivative is equal to 0. But everywhere the second derivative is equal to 0, there may not be an inflection point. For instance, look at the function y equal x to the fourth. If you take y prime, which is 4x cubed, y double prime is 12x squared. Notice y double prime at 0 is equal to 0, but this is not a point of inflection because the function y equal x to the fourth is concave up at all points. But I would still look at the points where the second derivative is equal to 0, and you might just see a point of inflection. Now, sometimes a point of inflection can be where the second derivative is undefined. Here is a case in point. We have the function y equal when x to the 1/3, the first derivative is equal to 1/3 x to the minus 2/3. So the second derivative is equal to minus 2/9 x to the minus 5/3, which is equal to minus 2 over 9 x to the 5/3. Notice that at x equals 0, y double prime is undefined. And just looking at the graph where it's undefined, there happens to be a change in concavity because y double prime, for instance, at 1 is minus 2 over 9, 1 to the 5/3. It's less than 0, so it's concave. Down. In fact, this graph is concave down for positive x. Take y double prime at minus 1. You see that that's equal to minus 2 over 9 minus 1 to the 5/3, which is minus 2 over 9 minus 1 to the well, it's minus 1, so it's more than 0, so it's concave up. So on this side of the graph, we're concave up. Now let's look at a graph that gives a position for t more than 0 of a particle. It's a function of time. I'm going to actually rewrite this as s equal 2t cubed minus 14t squared plus 22t minus 5. And we want to look at where the function is increasing or decreasing, and also the concavity. So let's take the first derivative of the function, which is equal to the velocity, and it is equal to 6t squared minus 28t plus 22. And this can be written as 2 times 3t squared minus 14t plus 11. And we can factor this into 2 times t minus 1 times 3t minus 11. Set that equal to 0, and it's 0 at t equal 1 and t equal 11/3. So to look at increasing and decreasing intervals, we'll again set up, since we're only considering t more than 0, we go from t equals 0 to t equal to 1, and then from t equal 1 to t equal 11/3, and then from t equal 11/3 to infinity, and we need to pick a test point. The test point for the first interval would be 0.5. For the second interval, I would pick 2. For the third interval, I would pick 4. And notice that we are looking at the first derivative is 2 times t minus 1 times 3t minus 11. and we need to look at the sign of S prime. At point 5, which would be 2 times a minus times a minus, which is more than 0, so it's got to be increasing. If we plug in 2, we get the sign of S prime is going to be, we got a 2 times, plug in 2, and we get a positive, plug in 2, and we get a negative, so it is less than 0, so the function is decreasing. Finally, we plug in 4, and we get a plus for the 2, we get another plus, and another plus when we plug in 4. So it's more than 0, so it's increasing. So, as you can clearly see from the graph, the function increases from 0 to 1. It decreases, by the way, this is 11 thirds, so the function decreases between 1 and 11 thirds. And then, as we predict, it increases from 11 thirds to infinity. Now let's look at the concavity. The second derivative of S, as you can see, is going to be 12t minus 28, which is equal to 4 times 3t minus 7, and it equals 0 at t equal 7 thirds. So to test concavity, we look between t equals 7 thirds and 0, and t between 7 thirds and infinity. Now pick a test point. And I would pick 1 for the first interval and 3 for the second interval, and look at the sign of S prime. Notice that S prime is 4 times 3t minus 7. Plug in 1, and we get 4 times minus 4 is less than 0. So it's concave down. Plug in 3, and you get 4 times 2, which is more than 0, and it's concave up. So as you can see from the graph, let me erase a little bit here. We see at t equals 7 thirds, which is about 2 1/3, which would be about right here, is a inflection point. That's where it goes from concave down to concave up. So as you can see, the second derivative predicts concavity, and the first derivative predicts whether the function is increasing or decreasing. Now, we're going to talk about a very simple second derivative test for local min and max at x equals c, where the derivative is equal to 0. If the second derivative is more than 0, it will be concave up and look like this, and predict that at that point x equals c, you'll have a local minimum. If at x equals c, the first derivative is 0, but the second derivative is less than 0, it's going to be concave down, and you would draw a picture like this, and it would be a, local max. It would be a local max. So just as our last example, we're going to analyze this function, x to the fourth minus 4x cubed plus 10, for increasing and decreasing intervals and concavity, and look at max and min, if there are any. Let's look at the first derivative. The first derivative is 4x cubed minus 12x squared. We can factor 4x squared out of this and get 4x squared times x minus 3 equals 0. So the zeros are x equals 0 and x equals 3. So to look at increasing and decreasing features, we set up our intervals between minus infinity and 0, between 0 and 3, and between 3 and infinity. Look at our test points again. First test point I would look at would be minus 1. Second would be plus 1. The third one would be plus 4. And now we'll look at the sign of y prime. Notice y prime is this function, and if we plug in minus 1, we get a plus times a minus. So that's less than 0, so it is decreasing. If we plug in 1, we get a plus, and a minus. It's still less than 0, so that is still a decreasing function. And then we plug in 4, and we get a plus and a plus, which is more than 0, so it should be increasing. And sure enough, we should be decreasing all the way to 3. Notice the function is decreasing all the way to 3, and then from 3 on, it is increasing. Now let's look at concavity. The second derivative tells us about concavity. The second derivative would be 12x squared minus 24x, which is equal to 12x times x minus 2. Set it equal to 0, and we get x equals 0 and x equal 2. And so there are potential points of inflection at x equals 0 and x equal 2. So now let's test this from minus infinity to 0, from 0 to 2, and from 2 to infinity, and pick our test points, which would be minus 1. By the way, this is x between 0 and 2. The test point would be 1, and the last test point would be 3. And so now let's look at the sign of the second derivative. Notice the second derivative is given by this function, so plugging in minus 1, for the first factor we get a minus, and for the second factor we get a minus. That's more than 0, so it's concave up. We plug in 1, and we get plus and a minus, which is less than 0, so it's concave down. And finally, plug in 3, we get plus times a plus, which is more than 0, and it's concave up. And sure enough, for the first part of this function, from minus infinity to 0, it's concave up. Then it's concave down between 0 and 2. And then it's concave up again. And you see the point 0 and the point x equal 2 would be points of inflection. Points of inflection. And that is on the video on concavity, and we'll be working these problems or problems like these in class.